Now, in this equation, let's do one step. Multiply the left hand side of this equation. In other words, take this equation. In this equation, let's multiply this equation by identity, this by a, this by a square, so on and so forth, and this by a power n. Okay? Let's do this. So when I'm going to multiply this equation by the first equation by a, I'm going to get what? I'm going to get c naught I equal to minus ab naught. This is what that you're going to get. What would be C1a? The left hand side becomes C1a. Okay. So the C1a will be what? It's going to be AB naught minus A square B1. So if I multiply this with A square, so it's going to be C2A square equal to, this term will become A square B1 minus A cube B2, so on and so forth. If I multiply this equation by say a power n minus 1, okay, so what you're going to get, c power n minus 1, a power n minus 1 equal to a power n minus 1, b power n minus 2 minus a power n, b power n minus 1. Okay? And if I multiply the last equation by Cn, a power n, what you're going to get? You're going to get a power n, b power n minus 1. And then what I want, just add all these terms. So when you're going to get c naught I plus c1a plus so on and so forth, cn a power n, what you're going to get? You're going to see, when I'm going to add these two terms will cancel. These two terms, all of these terms will cancel out actually. Okay, the a power n bn minus 1 is going to cancel out with this, and you're going to get to 0 actually. And what is this? This is nothing. The characteristic polynomial of the matrix A evaluated at A. And this gives equal to 0. And this completes really the proof of the theorem. I know that the proof of theorem is a bit messy, but it's worthwhile actually. That one must do it at least once in the life. Okay, and this is really what you call the characteristic. The Cayley-Hamilton theorem is that if you take a matrix and compute its characteristic polynomial and substitute that matrix into the characteristic polynomial, you're going to get always 0 matrix actually. In other words, a characteristic polynomial must always annihilate its matrix actually, from which you obtain it. Okay, so this is what really is the proof of it. What would be some of applications of it actually, the Cayley-Hamilton theorem. So for example, here is one simple application of the Cayley-Hamilton theorem. Okay, a fun application. So consider a matrix A that goes like 3, 0, 4, 1, 1, 2, and 1, 0, 3. Okay, this is matrix A. Let's compute the characteristic polynomial of A, x. In other words, let's compute the determinant of xi minus A. Let's assume that I made these calculations and it turns out to be the polynomial that goes like x cube plus 7x square minus 11x plus 5. So I'm assuming that you know how to calculate determinant and you can do these calculations. And this is what that you're going to get at. Now, the Cayley-Hamilton theorem tells you that when in this polynomial you're going to substitute 0, you're going to substitute A, you're going to get 0 actually. In other words, you're going to get x cube minus a cube plus 7 a square minus 11a plus 5 times of identity matrix equal to 0. Okay? And now if in this side of the matrix I multiply both sides by A inverse. Okay? A inverse. So if I multiply both sides by A inverse, what are you going to get? This is going to be A squared, this is going to be 7A, this is going to be 11 identity A, and this is going to be plus 5A inverse. And hence, I can explicitly, so here is the interesting thing, I can explicitly compute the inverse of the matrix using the higher powers of the matrix actually. In other words, the A inverse is going to be 1/5 of A squared minus 7A and minus 11 multiplied by the identity matrix A actually. Okay, so you got the inverse. So you might have seen the varieties of ways of finding the inverse of the matrix. You can compute really the inverse of the matrix using Cayley-Hamilton theorem through such matrix polynomials actually. Okay, so you can compute them easily. So this is what really is one of the fun application of the Cayley-Hamilton theorem. There are lots of other applications as well, but one fun application is that using the higher powers of the matrix A, you can easily compute the inverse of it.